Seems to be running. Welcome, ladies and gentlemen, and everybody in between, or not even on the spectrum, to the ICRAR Astro 3D Wednesday Astronomy Talk. Hello, hello, hello. First things first, I'd like to acknowledge the traditional custodians of the land on which we're speaking, the Whadjuk Noongar land, and pay our respects to elders past, present, and emerging. So what is ICRAR? ICRAR is a joint operation between Curtin University and the University of Western Australia. We're discovering the hidden universe through radio astronomy. Very exciting stuff. And Astro 3D is the ARC Centre of Excellence in all sky astrophysics in 3 dimensions. We can afford all 3, which is very exciting. We are unifying over 200 world-leading astronomers to understand the evolution of matter, light, and elements. So it's pretty cool. So the first things first, I want to point out that we have someone very cool to say, Dr. Sabine Bellstedt. Hello, Dr. Sabine. How are you?
Hello, hello. I'm doing very well.
Brilliant. So we're going to go into, is it science or is it art?
So here we have our science or art slide.
This is a strange one. It's very strange indeed. So is it science or is it art? I have no idea what this is. I have no concept. It looks like maybe I'm just wishing we could go outside more, but I keep thinking it's like a beach or something like that.
It definitely looks like water ripples. I can see that for sure.
Yeah. So, but it's going to be gravity waves or something. Like it's going to be something.
Oh, it also kind of looks like when you've got a big star in an image and it kind of has horrible ghosting issues all throughout. It looks a little bit like that as well. Or if you've ever tried to take a
So if our listeners wondering what it is, well, we don't know. Dr. Sabine and myself have no idea exactly what it is. And so you can always check it out at the @ICRAR Twitter handle, and you can put your guess in there, and we'll let you know Friday when the imps who are the tech imps behind this whole situation will be able to tell you what it is. Because they keep it secret. They keep secrets from us. Stupid imps. Whoa, not fair. Not fair at all. They're not stupid at all. They're very great imps. Otherwise, they'll just shut me off. My camera will just stop working instantly. They have all the power. But enough of this tomfoolery. I think we need to get straight into Dr. Sabine's talk. Take it away, Dr. Sabine.
Thanks very much, Greg. Well, I wanted to start off by showing you all this beautiful picture. And if you're anything like me, you will definitely have looked up at the night sky at some point. If you're lucky enough to be living in Western Australia, like we are here at ICRAR, the Western Australian sky gives you something beautiful like this. And of course, this is our Milky Way. This is the galaxy that we live in. And it might surprise you to know that almost everything that we can see in the night sky with our naked eyes only exists within our own galaxy. So everything that we can see lives within our own galaxy. You see stars, you see dust, and if you look even more closely, you might see clusters of stars or balls of gas that might produce stars. But because of that, it's perhaps unsurprising that for most of human history, we thought that what we can see in the sky is all there is to see. A few hundred years ago, we started seeing what were called nebulae in the night sky, little balls of gas. And in the year 1755, a philosopher known as Immanuel Kant made a very controversial statement. And he suggested that these nebulae that we're seeing out there in the sky with telescopes at the time could perhaps be what he referred to as island universes. And he suggested that it's possible that everything we see out in our own night sky, everything that is within our own galaxy, might actually be replicated in a galaxy outside of our own. This was seen as completely crazy and was very controversial. And actually, for many hundreds of years, people believed that that couldn't possibly be true. And it wasn't until around only 100 years ago that the first pieces of evidence came in suggesting that, yes, actually, whole galaxies exist outside our own, and not just a handful, but many, many thousands. In fact, Edwin Hubble was one of the first people to really look at galaxies. At this point, they were still referred to as nebulae, and made characterizations. So what you're seeing here on the screen is some of the earliest photographic plates showing real analysis of galaxies. You can see on the left there, it just looks like splodges. You can see it's like someone's painted paint all over a canvas. And all those little dots are actually galaxies. On the left, there are two images of what you can see used to be referred to as fuzzy balls of gas, and those are actually galaxies too. Fast forward around 70 years from the time that Hubble first started characterizing galaxies, we were able to send the Hubble Space Telescope, named after him, into space. And once the shutters of Hubble finally opened and let in the light, we were amazed with the spectacular images that we could see. This is an example of a Hubble deep field, as we call it, where we've spent hours and hours staring into the deep depths of the universe. And you can see a spectacular array of different objects. And here what you're seeing, except for perhaps one or two stars, everything there is outside of our galaxy, hundreds to millions of light years away. And you can see a spectacular diversity of objects. You can see things that we call disks, and you can see they've all got that kind of spiral structure. They're all quite blue to look at. And then you see a completely different kind of object with these kind of spheroids that you see. They're all roundish, they don't have much structure, and they're all very red. We can look at these two objects next to each other like this. Contrast this with what we call an elliptical galaxy. And these things are enormous, but there's almost no structure. It's all just one big cloud of stars. And so now the question is, what happened to these objects such that they have become so different? And this is a question that we try to ask ourselves using images of galaxies to try and figure this out. One answer to this question could be mergers. And so mergers are spectacular things that we see in the universe, where one, two, or at least two, or many more galaxies can collide with each other. Here on the left is one of the most famous examples of this. These are the Antennae Galaxies, and you can see they're just in the process of colliding with each other. On the right, you can see an example of where a collision has just occurred and it's leaving streams of stars all around the place. And we see evidence of this all over the place in different forms. Here, a galaxy merger has occurred. Another merger, you can see this is now much farther along, and all you're seeing are these poofs of gas coming all over the galaxy and stars. All the way down to a galaxy like this, where we can see a merger must have occurred in the past, but a lot of the signature of that merger is actually hidden. It's not until you really increase the contrast that, you can start to see some unusual features here. There's what's called a shell or a stream very faintly at the bottom of that picture. And both of those things are signatures or clues that at some point in the past, a merger has occurred. So we can see physically what's going on with these galaxies in their pasts by looking at the structural remnants of what exists in that galaxy now. But something that I find particularly interesting is to see physically what's going on with color. Color seems like a pretty straightforward thing, but there's an enormous amount of information that we can extract from the color of a galaxy. Let's go back to our picture of the night sky. Depending on how long you've stared into the night sky, or how well you might be able to see the screen in front of me, you might be able to tell that stars, in fact, also have different colors. Can you see that there are different colors here? You might see that some stars are a little bit more red, others might be a little bit more blue. And what that actually comes from is that that relates to age. So young stars are hot, and because of that, they're quite blue in color. Older stars, contrastingly, are much cooler, and they're quite red. You might have seen an example of how this kind of physics works on an everyday life if you've ever spent time looking at a flame. A candle is a really good example of this. The flame of a candle is hottest at its base, and it's coolest at the top of the tip. You might be able to see it in this picture. That hot part is blue to look at, and that cool part is much redder. And so that's exactly the signature that we look for in galaxies. Are they redder or are they bluer? But rather than just looking at a simple color, we are very lucky as astronomers that we have a whole wavelength range that we can analyze galaxies. So here's a plot just very quickly showing what wavelengths we associate with the electromagnetic spectrum. So in the colored section in the middle, you have the visible wavelength range, and that's everything that we can see all the way from blue through to red. If you go to shorter wavelengths than blue, you go through ultraviolet, eventually you get to X-ray, and finally to gamma rays. But if you head onto the other side, you end up in infrared, so that's slightly redder than red, then microwave and radio. And looking at galaxies across the breadth of these wavelengths can tell you something a little bit extra than just color the way that we can perceive it with our eyes. So let's take an example of a galaxy. I'm actually showing you a galaxy here of a study that we're working on at ICRAR. This is imaging and data that we work on a daily basis to try and uncover the secrets of the universe. And so here's a beautiful color image of a galaxy. And we want to ask the question now, what does this galaxy look like all the way through from the ultraviolet to the infrared? If I go at the edge of ultraviolet, this is now called far UV. And I'm showing the wavelength for those who are interested at the bottom of the slide. You can see the image is quite grainy. That's simply because ultraviolet is hard to image. But it's roughly the same shape. So you can see the ultraviolet signature there. Heading to a slightly longer wavelength, we're now in the wavelength range that can cause you sunburn. This is actually similar to UVB. So if this were right in front of you, you'd get very bad sunburn. But you can see that lumpy structure is starting to come through in this image in the UV. Head a little bit further down the spectrum, you can suddenly start to see quite a big of change in structure. If you've ever been to a bowling alley and there have been black lights on, this is the right wavelength for you to see in black light. You can see all those little clumps. These are now new stars that are starting to make themselves known at this wavelength. We now make our way through to the optical part of the spectrum, and it suddenly starts to look a lot more similar to what we're used to seeing in galaxies. Again, you see the clumpy stars, but you can start to see a lot of the features that I'm showing in the color image. Still in optical, we're starting to evolve, and now we're heading into our infrared. And you can start to see that a lot of that clumpy structure starts to disappear as the new stars no longer make themselves known. Even further, this is true. We're now in the near infrared where actually this is the same wavelength that your TV remote uses to communicate with your TV. So you really wouldn't want this much signal communicating with your TV because that would wreak all kinds of havoc. Further through, we're getting to longer wavelengths. The galaxy is getting smoother and smoother. And at some point, we end up in actually a heat. So at this point, the wavelength is the same as what your toaster uses to toast your bread. So that's that heat. So this is actually a hot signal coming off this galaxy. Still further, and you can see again, it's harder to make the measurement and it's getting more and more grainy. But now we've reached the point in the infrared where if you were to image it with heat imaging, this is the same wavelength. So you can see we're now covering a huge range of different wavelengths. And still further, you can still see that galaxy, but it's looking very grainy and very washed out. Until finally, we reach the edge of the infrared that we use on a daily basis for astronomy. And so you can see by looking at a large number of different wavelengths, we're now seeing a huge amount of information. And so we use this as scientists on a daily basis in the form of what we've called a spectral energy distribution. So if you take all of those images that I've just shown you in the different wavelengths, and we want to see how bright is that galaxy in each wavelength, we end up with this plot, and that is what is known as a spectral energy distribution. And if I go through these same pictures, you can see that orange star moving on this plot. And this is showing what it is that you're measuring with this sort of measurement. And you can see I've put the little pictures there to show what kind of wavelengths you're looking at. But this shape, this wiggle curve that you're seeing on the screen, actually has an enormous amount of information embedded into it. So exactly that shape is a clue as to how old the galaxy is, when the star was formed, and what kind of components that galaxy is made up of. And we can solve this shape just like a puzzle to understand the past of a galaxy. Here now, I'm showing in orange a few different examples of what we call a spectral energy distribution. Interestingly, they actually look a little bit like a constellation of stars. But all this is saying is if you take a galaxy with stars of different ages, you know exactly what this shape should look like. So if I take a galaxy that's 10 billion years old, which means that it formed most of its stars 10 billion years ago, then we get the SED shape that we see on the top left. Now we can try to see, how does that compare to the galaxy we just looked at? Okay, and you can see on the blue and ultraviolet end, there's a big difference, and this second peak doesn't even exist. So there are a few differences there. If we take a slightly younger galaxy, maybe one that's 5 billion years old, so this was formed just after halfway through the universe, maybe that gives us a bit of a better fit. You can start to see this infrared peak is starting to pick up, and there's still a little bit of a difference. So that's one way we can test it. How about something that's completely new, that's forming almost all of its stars very recently? So I've put here a recent galaxy as forming its stars 0.1 billion years ago, which is actually 100 million years ago. And you know, that might sound like a long time ago, but in the grand scheme of observations, this is a very young object. So let's see a very young object, how it compares to this. Okay, the piece of that puzzle doesn't quite look different. Interestingly, this blue part now has a much, much higher peak than what we saw before. And if you remember what we were saying before, blue means young stars. So the fact that this particular shape shows lots of blue is an indication that there are lots of young stars. Given we just said that's a young galaxy, this makes sense. How about now if we try a happy little medium and we test a galaxy that's about 2 billion years old? How does that look? A little bit closer. What do you think? Which of these do you think fits best?
Definitely 2 billion years. Absolutely 2 billion years. I put money on it.
Indeed. So in this case, we might think that, boom, the shape that fits 2 billion years fits the spectrum that we have been looking at from this galaxy. And that is enormously valuable because we can tell a huge amount of detail, even if it perhaps formed stars over a long period of time or a short period of time. We can tell that difference just by looking at the light. Now, the interesting thing is if you look at this galaxy, it's very big and you can see a lot of structure. But if you look closely, in the background, you can see lots and lots of other galaxies that are very small. And it's actually hard with our eyes, even with the best telescopes in the world, to see very much structure in these galaxies. But if you make the exact same measurement and you just look at how much light is in that galaxy in different wavelengths, it doesn't matter how small or big it is, you can apply the exact same technique in order to know exactly how old these galaxies are. Now at ICRAR, we spend a lot of time looking at an enormous number of galaxies. In fact, the kinds of projects that we work on spend looking at hundreds of thousands to millions of galaxies at a time. And the really interesting thing about that is by applying techniques like this, where we look at images all the way through the different wavelengths, we're able to learn some interesting things. We know that spheroidal galaxies, so these things that look round and often red, are very often the result of a merger, and it's completely disrupted the structure of a galaxy. So for those things that we can see structure, we now know that mergers play a big role in how they look. But by looking at the colors of these galaxies, we now know that a large number of these red spheroidal galaxies that we see in the sky formed most of their stars 8 to 12 billion years ago. Interestingly, that's the time in the universe where actually most of the stars in the universe were formed. If we then look instead at the disk-like galaxies, we see that they've been forming stars throughout the history of the universe. So our Milky Way, for example, has been forming stars for about 10 billion years, all the way through to smaller galaxies that are disk-like that have only started forming stars in the last few billion years and are very young. Putting this all together, we get a beautiful picture of where star formation occurred in the universe and how it is that what we see out there is so incredibly varied. That's it from me. I'll leave it for any questions that you might have.
Fantastic, Dr. Sabine, thank you very much. Now I'm going to be very mean to our listeners and our audience and take the first question myself. So I have a question that I want you to answer. I'm going to pick your brains. Now, you showed before that by looking at the light, you can work out the age of the galaxy. But how did you create the gauge that you know that's a 2 billion year old light curve or spectral curve? How did you know that's 2 billion years? The first one must have been gauged somehow.
Oh, absolutely, absolutely. And this is an enormous field of research that we have hundreds, if not thousands of people working on all throughout the astronomical community. And it requires many people of different branches to actually understand this. Interestingly, a lot of this doesn't come from galaxies as a whole, but it comes from individual stars. So if you look at an individual star, you've got many more things you can measure about it because it's close to us. You can measure the temperature, you can measure the chemical abundance, and from that you can actually determine how old it is. So if you know how old it is, you can then look at its colors and say, okay, we now know what this particular type of star looks like. If you sample stars across different ages, you can now do what is known as stellar fitting, where you can essentially add lots and lots and lots of stars together, and you see what does a galaxy's worth of stars look like. So you can model this essentially by saying, if we have a population of stars that's 2 billion years old, what do we expect this spectral energy distribution to look like? We compare that against the galaxy, and that's how we know, that one's 2 billion years old.
There we go. And that's a great answer. Thank you very much. Now, if our viewers want to ask a question, please write them in the chat and I'll get onto them. But we have one from Greg McCall. And Greg asks, when you say we look, do you mean your computers look?
Well, it means that a telescope has observed the universe, it's collected photons, it's gone through a CCD, and it's measured an image. So once upon a time, it was much more like an old school film camera where you had a photographic plate and you would make a recording of the image. Nowadays, it's all digital, much just like your digital cameras. And so then we see an image of the galaxies. With enough processing, we can then digitize that. And then, yes, absolutely, a computer does an enormous amount of grunt work to spend a lot of time looking at images, but most of that is done by the computer for sure.
So once again, computers can't do it on their own, humans can't do it on their own. So it's a wonderful marriage of two, biological and silicon. How wonderful.
For sure.
That's all good things are. Greg has another question. And how do gravitational waves fit into that spectrum?
You know what? This is the really, really, really exciting thing about gravitational waves, because the answer is they don't. So for almost all of the history of astronomy, every signal we received from the universe was part of the electromagnetic spectrum. And no matter what it is we analyzed, somehow it came down to a photon of electromagnetic energy reaching our telescopes. The amazing thing is, with the discovery of gravitational waves, a whole new world opened of information that has nothing to do with the electromagnetic spectrum, which is really exciting.
So all our viewers can go and become gravitational wave astronomers and teach us all of the next generation of the new exciting things we can find, with things like LIGO and all the other great instruments that are going to get built. That's pretty cool. Okay, a nice comment here from Peter saying, great presentation for the amateurs and for everyone else who aren't amateurs. So thank you much, Peter. I appreciate that. That was very good. Any other questions? Make sure you put them down. But while we're waiting for any more questions, though, I just want to point out that there's a very important bit of science and a bit of fun you can do as well. So on the 21st of June, so coming up on the winter solstice here in the Southern Hemisphere, the best hemisphere, you can take part in the world's largest online sustainability lesson about light pollution on the 21st of June. You can do a world record, you can be part of a world record and help scientists around the world map light pollution and the effects on the environment. So you can just type in, just search for on Google, I'm sure you know how to do it, world record light, and you'll be able to find it and you can be part of it. Or you can always ask us at ICRAR on Twitter and we can get the information as well. If you have any questions for Sabine, and later on, like you're sitting at home and suddenly you're thinking to yourself, oh, I should have asked that question. Why didn't I ask that question? My life is ruined. Then you can always, of course, ask Dr. Sabine herself, which is her Twitter handle, which is just be on the page down the bottom there as well. But once again, you can always ask at ICRA and we can get it onto her as well. So a question from Peter, over what period does it take for a merger or collision? I'm assuming he means of galaxies.
You know, it takes a very long time. Obviously, it varies. So in some cases, you might get little things that are sucked up by a big galaxy very quickly. But on the whole, it'll take many billions of years from the time that the galaxies first approach each other until we might call a galaxy merger complete or relaxed, which is the terminology that we use, but many billions of years.
All right, if there's no more questions, we may finish up there. Thank you very much, Dr. Sabine, for coming and talking today about this really interesting subject. It seems simple, and you realize how complicated it is, and it leads to this rabbit hole of information we can keep looking at.
Absolutely. Well, thank you very much for having me and for letting me share all of this stuff.
Oh, hang on, wait. We're good. Ben Q asks, are there any biases with deriving their ages as we look at higher redshifts?
Oh my goodness. That is a minefield of a question. And of course, Ben, yes, definitely. So for those of you who aren't familiar with the concept of redshift, we're very lucky within astronomy that we're one of the few places in the world where we can not only infer the past, but actually see it. So you might know that light takes some time to travel. And so because the universe is expanding and because the universe is big, things that are, very far away from each other have light that takes time to reach it. So there are things in the past where the light is only just reaching us now. The farther away or the farther back in time these objects are, the higher their so-called redshift. So astronomers, we often talk about the high redshift universe. What we're talking about is actually the early universe, the way that it was billions of years ago. So yes, we can apply this exact same technique to galaxies earlier on in the universe. And that's tricky because it turns out that galaxies earlier on in the universe are slightly different to how they are now. One good example of that is dust. So we didn't talk about it too much, but you will have seen, at least for lots of those disky galaxies, is that there's a lot of dust in galaxies. And what that does, it actually blocks the light from the stars. And so we need to do some very, very careful modeling to account for that, to say, given the amount of dust in a galaxy, here's what we expect the light of stars to actually look like. Now, we might think that dust, the way that we know it from galaxies around us, is universal. But if dust in the early universe is very different, then it means that we might not be accounting for dust in the right way in these galaxies, and we might be thinking that the galaxy is older than it actually is. So definitely, when you look at things in different redshifts, you can start to get little things like that causing a lot of trouble.
Amazing. Thank you once again, Dr. Sabine. And also, this will be the last of our talks. We'll be doing our regular talks anyway. We've been running them for quite a few weeks now, but we've got to wrap them up, I'm afraid. So thank you to all the viewers, and thank you to all our speakers who have come along and been part of all this, asking all your questions, delivering all the answers. It's been amazing. If you, as a viewer, want us to get someone to come and talk about something, send us an email, get onto us at ICRAR on Twitter, and we'll hopefully get some more talks up in the future. So thank you very much, everyone. And I'll just say good night from me and good night from Dr. Sabine.
Good night, everybody.
And we'll see you in the future. Bye.